good day everyone. So we are still here in our topic, Fundamentals of Conduction. Okay. So we have already tackled some fundamentals regarding this, and then um, we have some classification of heat conduction problems, the steady state, the transient heat transfer, the multidimensional, what else? The with or without heat generation, and what else? So after that, we've tackled the thermal properties. The thermal properties. What else? It includes the thermal conductivities and the thermal diffusivity, and we have also uh, some derivation of the heat conduction differential equation, especially in rectangular coordinate system. And then for this uh, video, we will gonna tackle the what we call boundary condition. Boundary condition. Yeah. So boundary condition. Okay. So boundary condition is basically refers to the um, condition at the boundary. So that's it. So it is the um, any existing condition at your boundary. Okay, so it may refer to the temperature, to the nature of heat transfer mechanism, the heat flux, and so on. So basically it refers to any condition at your boundary. So for example, you have, say we have this uh, wall. Say this is our system. So we have a wall here. Yeah. See, for example, that is a wall. And uh, at the uh, okay, so at this boundary, say this is our system. So at this boundary, we know the um, surface temperature at this wall. So we know this temperature. Say, let's call it T1, the surface temperature, or the um, inside temperature, the initial temperature of this wall. Okay, so that is your condition at the boundary, so that you have a certain value here of the temperature of your wall. Okay, so that is the what we call our boundary condition. Yeah, so the condition of your wall at that point is this certain temperature. Therefore, your boundary condition here is in terms of uh, specified temperature, right? Okay, and then meaning it is the temperature. I mean, the temperature is given at the boundary. Given at the boundary. Okay. So aside from the given temperature at your boundary, say we have another boundary condition in terms of your heat flux. Say it is specified that at the boundary, say this is your wall again. So at the boundary, you have a perfectly perfectly insulated uh, material. So you have your insulation here. So you have your insulation here. Therefore, the heat flux given at the boundary, if there is a perfect insulation, the heat at the boundary will be zero. So the Q at the boundary here is zero because you have your condition that you have a perfect kind of insulation here in your wall. Okay, so heat flux given at the boundary if perfect insulation. The heat out boundary will be zero. So this is your condition at the boundary. At this um, certain situation. Okay. So another situation, say we have um, say we only consider convection, or if convection is the only mechanism at the surface. So say we have once again our wall here. Okay. Then this is our boundary, and say if this is about convection. So if convection is the only mechanism at the surface, if convection is the only mechanism at the surface. So having this condition at your boundary, then we can now have say that our uh, um, convection is equal to the the um, Q conduction, right? So it's convection. And so you have this condition. If the convection is the only mechanism at the surface, then this heat transfer by conduction will be equated as the or equal to the uh, heat conduction in this plane wall, right? So that is your boundary condition. So aside from this, say for example, uh, say in terms of radiation naman, if the radiation is the only mechanism at the surface, then what? So if the conduction is the radiation. Oops, sorry. If radiation is the only mechanism at the surface, say for example, you have your Q radiation here as the only heat transfer mechanism, then your Q rad is equal to the heat transfer inside this wall, Q conduction. Yan. So basically that is the given condition existing at your boundary. So that is the what we called our boundary condition, right? So so another, say for example naman, we have a boundary condition specifically given at the interface. For example, you have a uh, series of walls. Say you have wall A and wall B, and then you have here your uh, certain condition is given. Condition. So say the condition here is given. Then um, this is the what we call the condition is given at the boundary. So this is your boundaries. Then the condition is given at boundary, right? So what else? So basically in heat transfer, it refers to the any condition existing at any of your boundary. Okay, so it can refer to the temperature, to the nature of heat transfer mechanism, or the heat flux, and any other thermal conditions. Okay, so we can also have the say we have a generalized, you have your generalized boundary condition saying that the heat transfer to the surface in all modes equal to the heat transfer from the surface in all modes. So that is your condition. Okay, so once again, when we say boundary condition, it refers to the condition at the boundary. So say this is our system, this is your boundary, and you have a given temperature of this point or of this boundary, then you have your boundary condition. Okay, so this boundary condition mathematically they provide um, additional information or given to our equation, to a differential equation, in order for us to solve for the arbitrary constants, right? So remember in our mathematics, okay, so we can solve for this arbitrary constant to um, or the differential equation as a whole, or in other words, a heat transfer problem in a medium is not complete without a full description of the these thermal conditions at the bounding surface of the medium. Okay, so when we know this arbitrary constants here, then we can now have the particular solution of our differential equation. So that's it. Once again, boundary condition refers to the condition existing at your boundary.